In the two previous videos, we talked about most of the important topics of the fundamental theorem of calculus and the definite integral. The concept of the definite integral, its computation, and calculating the derivative of an integral. We talked about all those. In this video, we're going to concentrate upon three advanced examples. 4.4, 4.5, 4.6. Here they are. Find the equation of the tangent line. Yes, we talked about these kind of problems a lot. However, this time the function is defined in terms of an integral. Calculate the given limit. Well, we talked about limit computation in chapter 2 and again in chapter 4, but this time we have a function defined by a definite integral. Determining the increase and intervals of increase and decrease. Great, we talked about those back in chapter 4, but this time we have a function given by the definite integral. Well, I think everybody saw that common theme is that the function is given by the definite integral, and that must have something to do with this formula over here. And you're right, we're going to use that one. So, okay. So for convenience, I'm going to copy that down here, down here, and then down here, so that I don't have to scroll up back and forth too much. Okay, how do we handle this kind of problem? Please remember how to find out an equation of the tangent line. You need it in this kind of form. Y equals to slope x minus x naught. Oops, this should be parentheses, plus y naught. So you have to find out first y naught by plugging x equals x naught. Number 2, calculate the derivative. Number 3, plug in x equals x naught to the derivative to find out the slope. And then you're through. Here x naught is given by x equals 1, so that's what you have to plug in. Okay. First, if you plug in x equals 1 right away, what happens? We are plugging x equals 1 right here. So do you have 1 squared plus 1 over there? Indeed. If you plug in x equals 1, we have 1 squared plus 1 over there. So you have an integral from 2 to 2. It does not matter what we have over here, because the integral is moving from 2 to 2. Top and bottom are the same. That function value has to be 0. So here it is. Y naught is 0. So this part will be 0. Okay, that was easy. And let's find out the derivative. And the derivative computation will be this formula over here. Sorry, I didn't want to scroll. That's why I copied it here, but I ended up scrolling again. Okay, alright. Let's take the derivative. And how does the derivative work? Here's my function. Just plug in x squared plus x, let's highlight this, x squared plus x in place of the t's, right here and there. That's what I got over here. And then by chain rule, you have to multiply the derivative of this x squared plus x. That's 2x plus 1. Minus. Do I have to bother minus? Actually, you don't, because even if you plug in x equals to 2, t equals to 2, derivative of 2 constant is 0, so whatever you're going to get, this is going to be 0 times something, so that's going to disappear anyway. So I don't have to worry about that part. Now, if I plug in x equals to 1, it is equivalent to plug in x equals to 1 over here in all these places. And that's not too difficult actually. Plug in 1 and some computation, you just get log of 1, which is 0. So you get slope equals to 3. Putting everything into the slope point equation, here it is. M is 3, x naught is 1, y naught is 0. So here's the equation of the tangent line in the slope point form. And if you expand this parenthesis, you're going to get the slope intercept equation. Y equal to 3x minus 3, it seems. Okay, you can pause this video and then go through the solution. Or actually you can read through the lecture note. So let's move on to the next example here. Calculate the given limit here. It may look like this fraction times this integral. Actually this is nothing more than 0 over 0 type limit. Actually this is the same as, okay, let's just copy it here. That formula turned out to be not so useful. It's the same as this integral over x squared minus 4. Oops. Because multiplying by 1 over x squared 4 is the same as dividing by x squared minus 4. But if I write it like this, then it's very difficult to read what's going on here. So it is customary to separate the denominator to 1 over the denominator form and multiply. But in any case, this is 0 over 0 type limit, so L'Hopital's rule apply. So what is the L'Hopital's rule? You have to take the derivative of denominator, which is just 2x, right? The derivative of denominator is just 2x. Derivative of numerator is gonna be, well, derivative of this integral, but then again, we know an awful lot about taking the derivative of an integral. Here's a formula given by the fundamental theorem of calculus and the chain rule. So let's go ahead and do that. Let's use L'Hopital's rule. So L'Hopital's rule applies and the denominator becomes 2x. The derivative of denominator is 2x. How about the derivative of the numerator? Just plug in x squared minus x, this one, in place of the t, then I have x squared minus x squared and so on. And then from this point on, just plug in x equal to 2, computation. What do you get? You get arctangent of 1, and arctangent of 1 is pi over 4. Oh, by the way, I forgot to talk about one thing when I stated that this is actually a 0 over 0 type limit. If you plug in x equals to 2, denominator becomes 2 squared minus 4, so 4 minus 4, that's 0. If you plug in x equals to 2 to the numerator over here, then that's integral going from 2 to 4 minus 2. So this is integral from a to a form. So this whole integral is going to go to 0 as well. So yes, this is a 0 over 0 type limit. Okay, I pause enough. Let's move on to the next example. I think this is the hardest one. Determine the intervals of increase and decrease of the given function, and here it is. So in order to find out the intervals of increase and decrease, what do? You have to take the derivative, and then you get an expression, and you have to do some factorization. Something like that. And then if that's greater than 0, what do you mean by that? That means, well, you have this factor, that factor, and that factor, and then you're going to get zeros. And then those zeros are critical points. And then you have to do some sign analysis to each interval. So the starting point is taking the derivative, and then the next point is factoring it. Let's remember that, and let's go ahead and do that. So let's take the derivative, which means plugging x squared minus x in place of excuse me, what am I talking about? It's x squared plus 1. Okay, plug in x squared plus 1 in place of y. So we have this, x squared plus 1 squared minus 4, x squared plus 1 squared plus 4. In this integrand, the top part, b of x, substituted in place of y, so we get that. That's not all. You have to multiply the derivative of this x squared plus 1, which is 2x. And then subtracting by 0, of course, you don't really have to bother subtracting by 0 because 0 doesn't change anything. The starting point is a constant, so derivative of 1 is 0, so 0 times something, that's all going to go down to 0. Alright, we have correct derivative now. All we need now is to factorize it. The denominator is pretty much all set. I don't really have to worry about it because this is this thing squared plus 4, so it never becomes 0. The denominator is already irreducible. I don't have to worry about it. Numerator, on the other hand, we have, a squared minus b squared form. It can be factored. And for some stupid reason, I did not use that shortcut method, and I just expanded out and calculated and then factored it again. Okay, this one works, but I just realized that my method over here is too stupid. So let's go ahead and do it in a little bit more clever method. So this is a squared minus b squared form. So x squared plus 1 minus 2, and then x squared plus 1 plus 2. So if you have a squared minus b squared form, then it's the same as a minus b times a plus b form. So here it is. And then if I simplify this thing, this is going to be x squared minus 1, and this is going to be x squared plus 3. And x squared plus 3 is already irreducible, square plus a positive number, so I don't have to worry about it. X squared minus 1, it can be factored further, and if you do that, you're going to get something like this over here. Okay. The method over here was a little bit stupid, but it works out anyway. And then here's a full factorization, and we have three critical numbers. X equals to 0 for my first factor, x equals to negative 1 for my second factor, x equals to positive 1 for my third factor. Maybe expand it a little bit. X equals to 0, x equals to negative 1, x equals to positive 1 from that. They all have multiplicity 1, so we're going to have sign change. In short, we are going to get something like this. Here, plug in some big number, x is 100 or something. Everything is well positive. Excuse me. So, in this interval, the derivative is positive, so original function is increasing. Excuse me. And then, all the factors have multiplicity 1, so we have sign change. Minus, plus, minus, also sign changes. And then we have decreasing, increasing, decreasing, increasing. So we completely determine the interval of increase and decrease by this diagram. Interval of increase, negative 1 to 0 and 1 to infinity. Interval of decrease, negative infinity to negative 1 and 0 to 1. We have local minimum at x equals to negative 1 and x equals to 1. Local maximum at x equals to 0. Everything follows from this diagram. Let's decrease the font a little bit so that you can see the entire solution. in a single viewing window.